Assalamu alaikum everyone. My name is Siyaan Qureshi. I'm a second year medical student, and today I'll be covering enzymes 2, so the enzyme kinetics lecture. Here are my contacts if you'd like to text me or send an email if you're more comfortable that way. If you have any questions or concerns regarding this session today. So here are the learning outcomes. I won't read through them all, but there they are for you. And so let's start. Firstly, with what exactly is kinetics to begin with? Well, kinetics is the study of rates of reaction. So another word for rates of reaction is velocity. So you can think of it as the substrates here. They're trying to reach the other side, the product side of the race, okay? And enzymes are going to help along by pushing substrates towards products. So in a sense, that's how fast they can run, their velocity in this race. And so enzymes, which can push substrates from the substrate side to the product side faster, will have a higher velocity, and those which are slower will obviously have a lower velocity. Hope that makes sense. So enzyme kinetics. So as you mentioned, rates of reaction can also be called as velocity. And the way to calculate it is either we look at the concentration. See these brackets, they simply mean the concentration of something. So this is the concentration of a product, and we can measure the increase of the product's concentration to figure out how much is being made, as in how much substrate has been made into product now, and vice versa. So we can look the other way around as well. We can see the substrate can decrease over time. We can measure that decrease. Either way is the same thing. Either we measure how quickly that substrates are getting to the product side, or how quickly products are being made, as in it's the same thing. Hopefully that makes sense. Um, and when we do these measurements, an important thing we need to know is that enzymes always remain a fixed amount. Sorry about this. They remain a fixed amount all the time. So when we make these experiments, changing the substrates concentration, we always keep the enzyme concentration the same. Um, and when we take these measurements, we do it at the start or near to the start of the reaction. This is called initial velocity. I won't go into nitty-gritties as to why we do that, but just make sure that you remember that initial velocity is how we measure enzyme kinetics, and it's usually near to or at the start of the reaction. Um, Two ways we can measure it is discontinuous and continuous. So as the name suggests, discontinuous is measuring the product formed over a set period of time, uh, repeated times. Okay, so it's sorry, let me start again. Sorry. So discontinuous, it will be non-continuous. So we basically have a start point and an end point, and we measure the set period of time and the concentration between those two. Whereas continuous, we continuously sample again and again. We keep taking measurements. So let's say every minute for 10 minutes. Okay. And back to discontinuous, we'd say we'll take a sample after 10 minutes or after 5 minutes, but we won't take samples every single minute. That will be continuous. Okay, the way we measure them, usually, the concentrations, is, well, actually, concentration can be hard to measure if you don't go to titrating and other different reactions. An easier way is actually looking at how much color something shows. So, for example, we had this substrate called chromogen. It's, I don't know why this keeps on happening. Chromogen, it's a colorless substrate, so it has no color usually, but the end product gives you uh, a colored product. Okay, so you start off with colorless and it becomes colorful, and the way we can measure this is with a colorimeter or a spectrophotometer. They're similar things. Don't worry about them. The point is that you can use this machine to check how colored the substance becomes, and obviously as the reaction progresses, it will become more colored. So here's an example of a graph which is taking these measurements. And let's say again, we had discontinuous. So simply be we started at 0. And let's say after 10 minutes, we took a sample. And then 0 to 10 would be our measuring, like the measuring time. We went through 10 minutes. Whereas continuous, we keep taking samples every 5 minutes all the way. And back to the point of initial velocity, we're interested in the start of the reaction because that's where we can really tell um, how much an enzyme actually wants to react and push those substrates into products. Because later on, the limiting factor is not actually the enzyme. It becomes how much substrate is left, maybe. Other examples as well. But the point is, again, we want to look at the initial velocity. So if there's any trick questions in MCQs, always look for the initial velocity when they ask you about enzyme kinetics. All right. One more point that Dr. Jada made in his, I saw in the transcriptions, was he mentioned this is a linear relationship here, like a linear velocity. I hope that makes sense. It's just a linear graph. It's just a line here. Whereas over here, you see it's tapering off. It's getting more curved. So usually initial velocities are linear. That's all. Nothing too important. Okay, the second objective would be Vmax and Km. Well, Vmax is simply the rate of reaction when all of the enzyme sites, active sites, are saturated. As in, this is the fastest rate of reaction that can occur with this enzyme. So that's typically when you have the highest, you put as much substrate as you can, and they're completely saturating all the active sites. Okay. So on this graph, you can tell, for example, you've got substrate concentration down here, and you have the reaction velocity. This is the initial velocity. As you see the V0. Why is this changing? V0. And Vmax is the highest rate of reaction. So as you increase substrate, the rate of reaction is increasing. All right. And you get closer and closer to that. You get closer and closer to that highest reaction rate when you have a higher substrate concentration. And the second point is that as you get higher and higher, it starts to slow down. I'm going to try and touch the mouse less. Sorry, I won't be able to move this pointer because it keeps on changing my slide. But as I said, the more you go up to the right, the more you go right to the substrate, the closer you get to the Vmax. And that line starts to taper off because as you get closer and closer, more active sites are being saturated. Whereas in the beginning, active sites are very empty and it's just limited on the affinity itself. So talking about affinity is usually measured by Km. And Km is simply another definition which they put out, which is simply that half of Vmax is Km. Just memorize that. That's usually an MCQ question. It comes up every single year. I remember we got it as well. So Km is half Vmax. Technically, it's the substrate concentration which yields half Vmax. But sometimes the question isn't worded that way. It simply says half Vmax. So just be sure about that because it tricked a lot of us last year. And the other point to know is that Km is an inverse measure of affinity. So actually, the higher Km is, the lower the affinity of the enzyme is to a substrate. And vice versa, the lower the Km, the higher the affinity. So in a way, it makes sense because look, we can look at the steepness of this graph here. So if Vmax was over here, I'll try not to move this, but if Vmax was further up here, it would be less steep. So actually, the closer and more early we hit Vmax, as in the lower Vmax is, the lower the Vmax is, the more affinity the enzyme has to that substrate. Okay, one more thing about this graph is that many different experiments are being ran using fixed enzymes. So again, fixed enzymes for these experiments, you don't change the enzyme, you're changing the substrate concentration. And that's how we got this graph. That's all. So we tried substrate concentration of 0 and you got 0 reaction. We tried it of, let's say, 100 and we got closer to Vmax. We tried it at 50, we got somewhere to here. We got to 40 and that was half of the Vmax. Hope that makes sense. This slide, don't worry about it too much. He did say he might test you. Just simply know this equation, but he won't try and ask you about, he won't go into too much detail with simplification and rearrangement. No, just know Vmax, just know this equation. I don't want to waste too much time on it, but do know it because he might ask you to substitute some concentrations in. That's all. This graph is an important graph, which he asks a lot about. And again, this might look a bit complicated, but I have some rules which might help you actually understand it. So we could look at it in the way this equation is showing us, but I think there's no point actually trying to do that. It's much easier if we just follow these steps. Simply two steps here, or two rules actually. The first rule is the lower the y-intercept is, the higher the Vmax. Okay, so this is our y-intercept. And basically what I'm trying to say is the lower this line is, the higher the Vmax. Okay, so an enzyme is able to react with is able to have a higher reaction rate, the lower this line is. If there was a line drawn over here, a line drawn over here in comparison, we would say that one has a lower Vmax. Okay. The second rule is that the x-intercept, the more to the right it is, the higher the Km is. And the more the x-intercept is to the left, the less the Km is. So again, back to this graph, here's our x-intercept, okay? X is like following the floor and y is going up to the roof, okay? So y is up and x is across. They say like X is walking, across the corridor and Y is up the stairs or something like that. If you remember maths, I don't know. Anyways, so the x-intercept is here. And our rule said that the more to the right we are, the higher the Km is. So let's say we had a line over here, intersecting over here. We'd say that this line is more to the right, so it has a higher Km. And vice versa, if it was to the left, we'd say that the enzyme had a lower Km, and the Km was the affinity. So in a sense, we'd say that if the line was over here, it has more affinity. If the line was over here, reaching over here, it would have a higher affinity. Sorry, let me just, yeah, more to the right, increase Km. So more to the right, increase Km, lower affinity. More to the left, decrease Km, higher affinity. Okay. This slide is simply just showing you that there's a varied range of kms depending on the enzyme and its substrate, and that's literally it. So don't try and memorize these, or no, there's no worry. Don't worry about that. Simply know that okay, there are lots of enzymes in our body, and they all have different kms. That's it. Isoenzymes. So isoenzymes, we need to know they catalyze the same reaction. They have different kinetics. They're found distributed differently in the body, in different tissues, and they come from different genes as well. Because you have these things called alloenzymes, don't mix them up. Those ones are the same genes, but they're modified slightly differently. Here we're talking about isoenzyme. Iso, the same reaction, but apart from that, they're different. Different kinetics, different distribution, different genes. Okay. So one example which we have to know is hexokinase. Hexokinase is found in pretty much all tissues, and it converts glucose into glucose 6-phosphate. All right, and it uses ATP to do that. Okay. Now, one isoenzyme of hexokinase is actually called glucokinase, and we find that primarily in the liver. And the liver doesn't actually use glucose that much for energy. Actually uses fatty acid. That's also something which I think is important in other lectures, which is a bit of a crossover here. We have to remember that fatty acid is actually what liver uses the most energy. Now, why is that important? Because hexokinase is not really that important for the liver. The liver uses fatty acids. It's fine. It doesn't need to make this glucose and use it for ATP and etc. No. What we care about here is that the liver has a big role in regulating glucose levels. And why is that important? Well, because glucokinase has a different kinetics. Okay, it doesn't have the same kinetics as hexokinase. Its kinetics are suited more for regulating glucose levels. So let's look at this graph and actually figure out what that means. Well, here we have hexokinase. Here's hexokinase. And here we have the normal fasting blood glucose of roughly around 5 millimoles per liter. All right. So hexokinase gets fully saturated at that level at 5. As in, like, this range here is more suited for it to work. And by 5, it should be activated. It should be converting glucose into glucose 6-phosphate, etc., and converting the glucose into ATP, basically. Whereas glucokinase, look at its graph. Its Km is all the way over here. As in, it pretty much doesn't get activated. It's not actually getting used up, not used up, but sorry, it's not reacting as such that much at such a low glucose level. So we know, like, what this makes sense. I would ask, I'm not sure if there's any participants here yet, but I'd ask you here, like, why do you think it's up here, this half Vmax, this Km? Because it's more suited, actually. It's more suited for this role, the role of reducing blood glucose levels. So when you're hyperglycemic, of eating a meal, etc., then glucokinase is going to come in and it's going to help you decrease that glucose level. So normal tissues will be using this type of Km over here, whereas glucokinase is much higher because it needs to be activated only at higher levels. Down here, it's not really necessary. Hexokinase can polar weight. Now, a clinical insight which Dr. Zeda wanted to show you guys was regarding isoenzymes, particularly the aldehyde dehydrogenase enzymes. So in our body, we have two, a low and a high Km version. All right. We know Km is the affinity. So low Km means more higher affinity towards substrate. Okay. So the one we care about more here is the low Km one. The high Km has other it has another role regarding like retinoic acid, etc. Don't worry about that. Right now we care about the low Km version, which is ALDH2. Okay. So when we drink alcohol, for example, none of us drink alcohol fully, but if someone drinks alcohol, then alcohol dehydrogenase acts on it, makes acetaldehyde. Then acetaldehyde will need to be converted by aldehyde dehydrogenase into other metabolites. Okay, so the ethanol to aldehyde isn't here. It's actually the buildup of aldehyde, because basically aldehyde can cause these symptoms here, like red flushing on the face and poisoning, etc. So actually, this slide was trying to show you that many Asians, they have a genetic defect. They have some deficiencies in the low Km version, the ALDH2. They have a low Km version defect or deficiency. All right. So that means that this conversion is not going to take place as much. And so they're only relying on the high Km version. Now, I'm saying we're only relying on glucokinase. All right? Like glucokinase has a higher Km, okay? But the hexokinase, the normal substantiate, like the enzyme which is always running in all the tissues, for example, it's not there anymore. Like the normal one to keep your blood glucose in its normal range. So in the same way, this acetaldehyde, this low Km version is not there. We're only relying on the high Km version now. So basically you get these symptoms, and that's pretty much it. And this is also a question he loves to put in his MCQs, by the way. All right, okay. Now, a quick review on metabolic pathways before we go into the steps and feedback, etc. I wanted to ask regarding these steps, if we're talking about getting to reactant 6, which step do you think is a committed step? This is, again, another question which always comes in the exam. The answer would be C. Hopefully, you guys all got that. Why is that? Because what we can see here, the committed step is the first reaction unique to a pathway. So until now, you have 1 till 2. This is a shared step. This is a shared step. But 2 till 3 or 2 till 4, now you're committing to one of those paths in the road, okay? One of those forks. So C, the enzyme of C, would be catalyzing the committed step, and therefore that's going to be the answer. In the same way, if I ask you what is the committed step for 3, then the answer would have been B. But we're talking about 6 over here. How to get 6? The committed step is 3 from 2 to 4. A similar concept is the rate limiting step. Usually, the rate limiting step is actually the same as the committed step. The rate limited step, for definition, is the slowest reaction of the pathway. So it's going to be the one which is like, if you inhibit the rate limiting step, that's where the major clog will be in the road. All right, like that's the traffic jam, the rate limiting step. So in any enzymes, any pathways, you have to know, whenever you talk about them, you have to know the rate limiting step. That's the most important thing usually. And that tends to also be the committed step. All right. Now the next part. Hope everyone's following me. So the next part is going to be 2 different ways to give you feedback on this on metabolic pathways here. Okay. So the first one would be end product, otherwise known as feedback inhibition. And these are usually allosteric enzymes. So again, the name makes sense. We have an end product over here, and all it's doing is going backwards, it's feeding back into the start of the reaction, and it's just trying to slow it down. That's it. It's like we have so much of this already, let's slow it down. So end product or feedback inhibition. That's it. That's also negative feedback as well. Hope you guys can see that. Now this B over here, it's giving you the example of ADP and ATP. By the way, all of these are like, you can take this as a glycolysis pathway. These are just like simplified versions. All right. So in this one, we have A, it's going down to B, to C, to D, to E. Okay. And then it's going to give you CO2 and H2 at the end. All right. We don't care about that right now. What we care about here is that E is going to convert ADP into ATP. And ATP is what we want. All right. And because we want ATP, and we have ATP now, is also kind of acting like end product feedback. It's going backwards and it's saying, all right, we have ATP, let's slow it down. We don't need any more. Don't waste our energy, don't waste our resources and making more. We already have it, okay? Likewise, if we have we have high ADP, ADP is usually high when ATP is low. This is the ADP to ATP ratio, which I hope you guys have seen in other lectures. If not, this is a little introduction here, that's it. Basically, when ADP is high, we're in a low energy state. So we want more ATP to be made. And therefore, this is going to actually it's going to promote this step one till two, A till B, to actually go back and make glycolysis to give us ATP. That's it. So ATP, we already have high energy. We have a high ATP to ADP ratio. We want to slow it down. ADP, we have a low energy state. We want more ATP. We're going to promote glycolysis. That's it. This is an example of substrate level regulation. Basically, the substrate is going to act on the enzyme itself at the active site. What's important is that substrate level it's acting at the active site along with the other substrate of A. And that's going to actually help either boost or activate or inhibit this reaction. On the other hand, allosteric, I put this as a question mark because I'm not sure exactly which one the lecture wanted you to focus on, but actually ADP and ATP also act as allosteric promoters and inhibitors as well. And it's the same pathway again, it's the same feedback. So ADP will act allosterically and ATP will also act allosterically to also do the same thing, promote and reduce. And I'll explain the mechanism in the next few slides. So don't worry about that. Okay, the last point, and I think the least important, is actually positive feedback. We don't have too many chemical reactions which we care that much about, nor will be tested on regarding positive feedback for biochemistry as such. It is in physio and many other examples, but for biochemistry, it's just a short mention basically. So I'll quickly cover this. I think he was trying to explain committed steps and basically how committed steps, like you jump into it and you want to go along with it, all right? So for example, like glucose to pyruvate, okay? We have fructose 6-phosphate, and we want to make fructose 1,6-bisphosphate. So phosphofructokinase here, it has lots of these, promoters and inhibitors, activators, whatever you want to call it. And one of such is 2,6-bisphosphate, which is also made in this direction. Like you go in this direction, and there's many other reactions. I won't cover that right now. It's out of the scope of this lecture. But the point is that basically, this is trying to make sure you go one way, if that makes sense. So all it's saying is that the more reactants you have, the more you're going to try and go along with this direction of the reaction. That's all. And you're just trying to make sure that A goes to B and B doesn't go back to A. That's it. So actually, when you make B, B might make something else, which is then going to go back to A and say, let's make more. That's it. Okay? Don't focus on it too much. When you guys do the phosphofructokinase 1 and 2 enzymes, etc., in other lectures, that's all you have to know. Don't worry about it over here. Okay. That brings me to the allosteric enzyme product inhibition. So basically, I want to explain now what exactly are allosteric enzymes and what are they used for. Well, the main thing we have to know is that they're found usually at the committed step. Also, usually the rate limited step. I told you, these two usually go hand in hand, usually. And so in this example here, we have A to B, and this A to B is the committed step and the rate limiting step. So usually we'll find an allosteric enzyme there as well, E1 over here, okay? E1 can act like a catalyst, as we know here. It's acting like a catalyst for this reaction. It can also act like a sensor, okay? Dr. Joda's words with sensor. What does he mean by that? Well, basically, it's going to pick up on the concentration of the F over here, end product, which is going to go back, and it's going to act like an end product feedback, okay? And so it's sensing the concentration of the final product. And when it senses that concentration, if it's slow, it will carry on. If the end product is high, the concentration is high, it will actually slow down the reaction rate of A to B. So how does this happen? Well, F is going to actually bind to an allosteric site, okay? An allosteric site is different to the active site. This will be more, I'll explain it more in the next slide. Just know that basically it's acting as a sensor. It's picking up the concentration of F. And if the concentration of F is high, it will slow down the rate of reaction because we already have F. We don't need to make more F, okay? That's it, okay? And one more important thing to know about this is that the kinetics for an allosteric enzyme are actually sigmoid. But what does sigmoid mean? Well, here we have two graphs for the kinetics of the enzymes. This one is a hyperbolic curve. So this is how Michaelis-Menten kinetics looks like a hyperbolic curve, okay? You see, it's initially kind of steep and then it flattens off, okay? And we can take an initial velocity if we wanted to from over here, all right? And then on this side is going to be the sigmoid curve. Sigmoid, they say like it looks like an S. I don't personally see it, but like apparently this is the S shape over here. So yeah. Anyways, hope that makes sense. Just remember hyperbolic, it's becoming like this curve, and sigmoid looks like an S. It's curving up and down, okay? It's curving in this way and in that way. It changes its curves, okay? So yep, allosteric enzymes are sigmoid in relationship, and Michaelis-Menten enzymes, they follow Michaelis-Menten kinetics. Okay, so E2, E3, E4, E5 would follow the Michaelis-Menten curve, and E1 we said was the committed step, the rate limiting step. It has allosteric enzyme over here controlling these. Okay, that one would follow the sigmoid curve. Now, how do they actually work? Well, we have to know that they have several subunits, and actually the several subunits they bind to the substrate cooperatively. So it's not just like one piece, like like one lock piece, and then the key goes in and starts it. No, you have to have many different many different subunits, okay? And each subunit is going to work together to actually hold the substrate together, okay? And those subunits are regulated by either activators or inhibitors, all right? So activators and inhibitors they're all classes of effectors, okay? Don't mix it up. Effectors change the way an allosteric enzyme behaves, and they could be activators or inhibitors, okay? And they bind to their own allosteric site, not the active site. That's a very important thing to mention and remember, because many times they're trick questions. They'll write everything correctly other than this last point. They bind to their own allosteric site. And we can see this in this little cartoon diagram, okay? So the substrates are here, and we have a regulatory molecule over here. And this regulatory molecule is actually an activator, okay? So it binds, and it's giving space. It's actually changing the subunits to actually allow for this binding to happen for the substrate and the enzyme to make an enzyme substrate complex, okay? So this is a positive effector, otherwise known as an activator, okay? And over here is an inhibitor. So we had these subunits, and basically the molecule, the inhibitor or the negative effector, either way, don't worry about it. It's going to actually cause an inhibition. It's going to make the active site conform in a way which is actually harder to bind to. Okay. So we have activation and deactivation. Hopefully that all makes sense. And the final thing as well is that we have to know that each subunit has two states. Okay. A tense state and a relaxed state. So that's given by T and R. T for tense, R for relaxed. And the T state, the tense state, it's like it's all tensed up, okay? It's got low affinity. It doesn't want to bind. You can say it's scared, okay? It's scared. It doesn't want to react with anyone. It wants to be left alone. All right. The relaxed state, it's happy-go-lucky. It's just, it's just waiting for someone to arrive. It's waiting for a substrate to come and bind to it. So relaxed, high affinity. It's very happy. It's very friendly. Okay. Tense, it's nervous. It's shy. It doesn't want to talk to anyone. All right. So when a substrate binds, here we have an enzyme by itself. It's very tense. It's leave me alone. Okay. Don't touch me. When a substrate comes to try and bind to it, one might actually bind to it. Okay. That will actually cause it to become relaxed. And that will allow for the other substrates to bind to it. Okay. So allosteric enzymes usually start off tense. They start off in the low affinity state. And when a substrate binds, the first substrate binds here, it will actually make the subunits start to become all relaxed. And then other subunits, they're all relaxed now. So then substrates can bind to the subunits now. And then the enzyme can then catalyze the reaction. Okay. So once this catalysis has happened, once the substrate, then again, sorry, once the product's made and it releases from the enzyme, we go back to nothing occupying the sites, the active sites, and so we go back to the tense state again. Okay. So we have this interaction between substrate and enzyme. The second reaction we have, sorry, the second interaction we have is between the effectors and inhibitors. So as I mentioned over here, we had these activators or inhibitors, all right? So basically what they do is they bind to the allosteric site, okay? They bind to their own allosteric site and they do the same thing as what the substrate was doing. The substrate was binding to its active site and then it's causing it to go relaxed and letting other substrates bind, okay? Similar thing here, but the effectors and activators are binding to their own allosteric site, okay? Otherwise known as regulatory subunit, because it's regulating the function of the enzyme, okay? So regulatory, otherwise known as allosteric, okay? It is not the functional subunit. It's not the subunit that's actually causing the reaction to take place. It's simply just regulating the speed, the rate of the reaction, okay? So an activator, how it works is it actually bind and stabilize the R state. So that relaxed state, we see this one here, the substrate binds to an enzyme and makes it relaxed. This activator will come along and will actually bind to its own allosteric site. Let's say over here, not the active site, somewhere else. It'll bind to here, and it'll stabilize this enzyme into the R state. So now, even though the enzyme then may release its product now once it catalyzes the reaction, it will try and stay in its relaxed state. So it's actually allowing for more substrates to join because you don't have to get a kick-starting process here. You're getting the activators to actually stabilize the R state and keep it there. And you can guess now what the inhibitor will do. It will bind and stabilize the T state. So if an enzyme is found in the T state with nothing joined onto it, it will try and actually join on the allosteric site. The inhibitor will join and bind to the allosteric site and keep the enzyme from ever wanting to change to the R state, from trying to stop any of this from occurring. Okay? And this is just simply the whole thing in action. Okay? So you just have to apply what we did so far into a question now, okay? So if the not a question, it's an example, okay? So line one, this blue line here is it's simply going to be the enzyme with no modulation. Nothing is happening to it. This is how it is normally, okay? No inhibitors. Here we have the sigmoid relationship. So we know it's an allosteric enzyme, okay? And over here now, sorry, let's say two first. We have a high ATP. So we have 1 millimeter, 1 millimole of ATP. That's quite high, okay? So now look at this pathway. We know the ATP in the high state, we have ATP of high energy. We don't want to cause more glycolysis. So we're going to try and slow it down, right? So it's actually going to act as an inhibitor, an allosteric inhibitor. So it's going to bind to its allosteric site, and it's going to do what? It's going to stabilize, we said, the T state. Okay, so ATP is going to bind to this is I think PK1, and basically it's going to bind there, and it's going to try and keep it in its T state. And what's that going to do? It's going to bring down our reaction rate. Look at this. It's coming down here now. So we had this Vmax is still the same. Okay, Vmax is still the same. If you go competitively, if you increase and increase and increase the amount of fructose 6-phosphate, we're going to get to the Vmax. But the Km now, look at the Km. It's significantly reduced, right? Sorry, my bad. The Km is significantly increased. The affinity is reduced. Okay. Does that make sense, right? The fructose 6-phosphate concentration is at 1 over here. Over here it's only like 0.2 maybe. So the amount of concentration we need to reach half Vmax is much higher now. Okay, it's trying to compete and fight. It needs to be at a high concentration. Basically, the affinity is lower now. Okay, and when we add a positive modulator, so they're trying to say is basically an activator to this inhibitor. Okay, we had this inhibitor of ATP, and now we're adding an activator. You're actually going to increase that graph again. You won't reach the full because we still have that ATP there, but we're going to increase it to some degree because we're fighting that. Now they're fighting each other. We're adding, for example, over here, we're adding AMP. So in the same way I explained that ADP and ATP are going to fight each other, now we have AMP. AMP is also going to fight because AMP again is the non-phosphorated version, is like the monophosphorated version. Okay, ATP is the very phosphorated, it's like the high energy. AMP and ADP are going to be low energy. So we have low energy versus high energy. Here we go. So it's going to balance out somewhere here. So that's it. Hopefully that graph makes sense. If you guys have any questions, then let me know. Okay. So again, this is a similar thing, similar graph here. It looks complicated again. We don't need to focus on all of these steps. We just need to see the same thing happening. Here we have the same reaction over here, okay? And all we're seeing here is that basically this end product, this pyruvate is going to come out. It's going to make ATP and citrate. And ATP and citrate are going to go back and negatively feedback again. It's going to do end product feedback. That's all. And because this is again such an important reaction, this is the committed step and the rate limited step. Okay. Another thing as well is that the pentose phosphate pathway can also come out from here. So the point is that this is very regulated. This step is very regulated. Okay. So that's why we have all of these steps to make sure it's regulated. That's it. Okay. Don't focus on it too much. Again, this is the topic of another lecture. Critical insight. This is simply saying that here we have this enzyme, PRS. Don't even focus on the whole name, just PRS, okay? What does it do? Well, basically, it's an enzyme which is in the pathway for purine nucleotide synthesis, okay? So it's going to make purine nucleotides, okay? And some people have a mutation which leads to the loss of their regulation of this enzyme. That's it, okay? So this whole allosteric control we talked about over here, you know, this R states and T states, all you need to know is here that someone has a mutation which leads to a loss of this regulation. That means that basically we might always have our enzyme just stuck in R state or such, or maybe the T state can't, like the inhibitor is not being able to actually bind or whatever. We don't really care too much. We just have to know that basically we have no control anymore. Okay. And no control over this regulation means overproduction. We just keep on going, keep on going, keep on going into the product. We have no end product feedback anymore. And so this leads to uric acid building up in the joints, etc. And this is a scout. Okay. Again, this whole disease will be covered in another lecture. Just know again, this is simply a loss of regulation. So three factors we have for the enzyme activity. Enzyme 1, enzyme 2. Sorry, enzymes 1 and enzymes 2. I'm sorry. I'm so sorry, guys. So enzyme 1 lecture will cover the first and second factors, okay? And I'm covering enzyme inhibitors. So hopefully you guys have covered this from the first lecture, and this lecture will cover the inhibitors now. So what are inhibitors? A very quick recap, I'm sure you guys know. Simply, they're chemicals which reduce the rate of enzymatic reactions. All right, we know that. They work at low concentrations. Why is that important? Because low concentrations mean they're going to be more efficient. Okay, we don't have like high concentrations of so many chemicals. Things are toxic. No, you know, so we want low concentrations. They're specific, so they catalyze specific reactions, which means you can regulate them. They're not just reacting, causing mayhem on all our reactions. No, they're all tightly regulated and bind to specific things. Okay, they block and they try and slow down the reaction, but they don't denature the enzyme. That's very important. Okay, because these are all physiological. The point is that these are physiological inhibitors. They have to work at low concentration. They have to be specific. They can't denature enzymes. All right. Okay. And many of such inhibitors, they could be poisons, medications, etc., toxins. They could affect the nervous system. Okay. So we need to know two types of inhibitors: reversible and irreversible. Firstly, reversible, they usually bind covalently. Covalent bonds, if you guys remember from chemistry in high school, they're very strong, okay? Covalent bonds are extremely strong and they're hard to break again. So irreversibly, they bind, and over time, the more and more you add this inhibitor, it just gets worse and worse. That's pretty much it, okay? Like for example, like CO2, carbon monoxide and hemoglobin, okay? It just binds, it does not leave. Like it doesn't leave until the RBC dies, okay? So reversible, on the other hand, the weaker interaction. And that makes sense, okay? We want to reverse it, so it has to be weaker. It can't just bind so covalently and strongly. No, we want it to reverse, it's going to be weaker. Such interactions are usually, some examples are charge-charge interactions, okay, like positive and negative things, okay, hydrogen bonds, hydrophobic interactions, etc., okay. And three types of reversible inhibitors are competitive, non-competitive, and uncompetitive, okay. So I'll cover these three separately. Again, a quick recap on basically the rules for the line Riefer-Burk. I'll come back to refer to this if need be. So firstly, let's talk about the irreversible. So we have these irreversible ones, okay? So they bind tightly, covalently to the enzyme, permanently inactivating it, okay? I think I covered all that. It makes sense. And examples are nerve gas and pesticides. So as it's like nerve gases are going to like interrupt your nervous system. Pesticides, they do the same thing. They act on acetylcholinesterase and all the neuromuscular junction, etc. Okay. Yeah, here you go, acetylcholinesterase. Okay. So it's going to basically bind to that enzyme and it's going to stop transmission because you're going to bind here and you're going to stop the esterase. So I don't think you have to know about this. Just know this example. That's all. Reversible competitive. So what they're going to do is they pretty much look almost like the actual substrate. Okay, so we have the enzyme, we have the substrate. All they're going to do is they're going to mimic. They're going to look almost like the substrate. So we call them structural analog. Analog meaning like similar or same, and structural structurally. Okay, so they look almost the same as each other as substrates, and they're going to basically compete and fight for the active site. I'm sure you guys know a lot about competitive inhibitors already. And all you need to know about this aside is that, okay, the more substrates you add, the less the inhibition effect will be there because you basically added more people. Like let's say you have two armies, they're fighting each other for the active site. You add more and more troops to one side, they're going to win. That's pretty much it. Okay. So you have substrate and you have inhibitor, and they're both competing for the same site. And the more substrates you add, the more it's going to bind to there. Okay, that's all. Some examples we can know. Simply one example actually is statins. Statins are given for like hypercholesterolemia, for example. So you have a lot of cholesterol synthesis. Okay, you have a lot of cholesterol synthesis. How do you slow it down? Basically, you just add an analog to a structural analog to the substrate of HMG-CoA. Okay, so you have HMG-CoA. It's going to be used in the pathway to make cholesterol, and all you're doing is you're going to add a pretend cholesterol. Sorry, my voice is leaving. So those are statins. For example, Lipitor and Pivacol. Don't worry about them. Just know statins. In the exam, he's going to say statins can be used for, and there you go. There's your answer to competitively inhibit HMG-CoA reductase. So that's the enzyme which is converting HMG-CoA into all the metabolites which are going to be used for cholesterol synthesis. Okay. Now the lining for Burke graph again. When I first looked at this, it used to like actually phase me. Like remember last year? I remember last year it was like actually like, what is this? But again, just stick to the rules I told you. Here are the rules again. Lower y-intercept, higher Vmax, and x-intercept more to the right, increase Km. Okay, so y-intercept we can say is inverse. Okay, and x-intercept it goes the same way. Or we can say if you count x-intercept towards affinity, then it's going to be inverse as well. Either way, whichever one makes more sense and sticks with you, just stick with that. Okay. So here's the graph again. And let's look at the y-intercept first. Here we have the y-intercept, and we can see the y-intercept. We said that that's the Vmax, okay? That's symbolizing Vmax. That's 1 over Vmax, okay? And we said that the higher the Vmax would be, sorry, the higher this intercept is, the higher the Vmax, sorry, the lower the Vmax would be, okay? And the lower the intercept, the higher the Vmax. We can see this is the same, right? These lines are all passing to the same. This is no inhibition. This is a bit more inhibition. This is even more inhibition. And they're all passing the same intercept. So they have the same Vmax. What does that mean? Well, we had those two armies, they're fighting and fighting and fighting. But in the end, if you say you have a troops of a million and you have a troop of one, then the active site is going to be one-sided, okay? The active site is going to be fully saturated by the substrate. The inhibitor won't be able to fight it because if you increase that concentration from the substrate side, it doesn't make a difference anymore. The rate of reaction will reach its Vmax, its highest velocity. Okay, and Km we said would be on the down here, the x-intercept, right? We said the more to the right it is, the more Km is. Okay, more to the right, more Km. And Km, the higher Km is, the lower the affinity. So we know that over here is our line for no inhibition. It's actually starting over here. And we added the inhibitor, it moved to the right. We added more inhibitor, it moved more to the right. So the more inhibitor we add here into this competitive inhibitor, the more inhibitor we add, the more inhibitor we add over here, the more that the Km is increasing. The more Km increases, the less affinity the enzyme has to the substrate. And that makes sense, right? Okay. Now, non-competitive. So we have non-competitive and we have uncompetitive. So this is like one thing which people try to get their head around, and sometimes they mix around. And in the stress of the exam, it's very easy, but they just mix it up in the stress of the exam. I think I have as well. So don't worry about it too much. Just focus with me over here, okay? Non-competitive, basically they bind to domains other than the active site, and they don't interfere directly with substrate binding, okay? They bind either to the enzyme or the enzyme substrate, okay? So I put these little, whatever you want to call them, signs over here. And basically you can bind to the enzyme or the enzyme substrate. You can bind to both of them, okay? And at least no product being formed, all right? Um, I hope that makes sense. Again, if anyone has any questions, please stop me at any time. Although I think I'm reaching the end of the slides. Here's the graph for it. So as we said, it can bind reversibly. They can bind reversibly to either the enzyme or to the enzyme substrate complex, both, okay? And this is all reversible, okay? Now, the point is that these are all reversible reactions happening here. The two arrows mean they can go forwards and backwards. So what does that mean? Well, it's saying that we have no effect on Km because we said it's not binding to the active site, okay? It's not directly interfering with substrate binding. It's simply just it's just binding here and just being a nuisance. That's all, okay? It's non-competitive, okay? It's not competing for the active site. And so what does it look like? Well, we say it's no effect on Km and the Vmax decreases. Okay, what does this look like? Well, here's our Vmaxes. And where's the beginning one? This is the normal. The yellow line over here is no inhibition. And we're seeing the Vmax, the intercept is increasing. Okay. And our rule was that um a higher y-intercept corresponds to a lower Vmax. We said the inverse, okay? So here's our normal, and here is inhibition, and here's even more inhibition. And we can see it's increasing in height, okay, on the axis. And we said that's going to be a lower Vmax. And that's what the slide says, okay? Whereas in Km, this is quite close. We're going to say these are all lining up in the same place, okay? In reality, it's a bit messy, but let's just say these are all lining up in the same place, okay? And this is the graph he will use in his examples and in his questions as well. So don't go nitty picky and start trying to appeal this. He won't appeal this. This is the same, okay? And so what we're saying over here is that the x-intercept down here is pretty much in the same area. So we're saying the Km is the same. The affinity is not being affected. The affinity is not being affected here. It's just reversible reactions going on here and there. But otherwise, the Km, the actual affinity itself, is fine. Basically, what's happening here is you have a pool, you have, let's say, 100 enzymes, okay? And some of them are being thrown into enzyme inhibitor complexes, and some are being thrown into enzyme substrate inhibitor complexes. And all that's happening now is you just have less available enzyme to actually work over here. That's all. So because you have this inherent non-competitive inhibitor there, is present. No matter how much you increase that concentration, you can keep on increasing, but some of it's kind of just trapped in this little loop, you know. You see this loop over here? It's just trapped there. And they're not competing, actually, they're not actually competing with the substrate. They're not analogs. No, they're just binding to somewhere else and stealing the enzyme away a bit. That's it. Okay, so that's why you can't reach the highest velocity because some of it's still stuck in enzyme inhibitor or enzyme substrate inhibitor forms. And because adding more substrate is not actually affecting this reaction, this interaction. So it doesn't make a difference, regardless. That's it. Again, if there's any questions, please let me know. And I'll move on to uncompetitive. So this is going to be our last slide, our last part, basically. So uncompetitive reversible inhibitors, what are they? So we had non-competitive, which was when they're binding to the enzyme substrate complex, as well as the enzyme itself. Uncompetitive only binds, see this and this one? They're binding to both, okay? Over here, we're binding to only uncompetitive inhibitors. Wait, sorry, let me just quickly go over this. I just missed this out, my bad. Um, non-competitive inhibitors examples are lead and heavy metal. That's it. Don't worry about it. That's all. Um, he might mention this. So just remember that lead and heavy metal are non-competitive inhibitors. No matter how much you increase the the substrate level, it's going to be stuck in lead and heavy metal. Okay, they're going to steal the enzyme away. Okay, now I go back to this uncompetitive inhibitor. So it's binding to the enzyme substrate. Okay, and when it binds to enzyme substrate, again, it's not happening at the active site. It's stealing. It's stealing this enzyme substrate from another site. Okay, it binds to another site and it's stealing the ES. So it's not letting it be. It's basically blocking it from making products. Okay. So over here, it's just taking it a different way. It's just diverting it the wrong way, and now it's lost. It's just lost. Okay. If you have 10 concentration of an inhibitor, you just have 10 enzymes lost now. Okay. Over here, it's not trying to lose it. It's basically just it's binding and stopping it from releasing. It can't make its product anymore. So you have the enzyme, you have the substrate, it binds. Now you have the inhibitor. The inhibitor binds, and basically you can think like it's hugging on to the substrate. From a different site, it's hugging on, and it's not letting the substrate become a product. Okay, it's just stopping it. So it's uncompetitive. Okay. Um, it can't be overcome by high substrate concentration. Again, like non-competitive, it's not competing. So the only one that competes is competitive, okay? Uncompetitive and non-competitive, they can't be overruled by a high concentration of substrate, okay? Um, and here we have the graph for that. So here is the normal, okay? And if anyone's there, could you tell me would what would this increase mean over here? Okay, so this increase of the y-intercept will simply mean that we have a higher Vmax, sorry, a lower Vmax, and over here would be an even lower Vmax. Okay, so the more we increase over here, the more Vmax is decreasing, and that's what we see on this. And over here now in the Km, so we started over here, and we're going more and more left. We're going more and more left. Okay, we said the more left we go, the lower the Km becomes. Yep, the more left, the lower. The more right, the higher. Okay. So Km is decreasing over here. And a Km decrease, what did that mean? We said lower the Km, the higher the affinity. Okay. So just to quickly recap it again. I'd say this is like the highest yield part of the lecture. This is where they ask you the most. Okay. These three slides, irreversible, they're binding irreversibly, usually covalently, okay? Such as nerve gases and pesticides and some really bad poisons and toxins. Just think of like what what's really hard to counter. Irreversible, right? It's stuck. It's just stuck now onto your enzyme. Going to cause a lot of havoc and mayhem. Reversible, you have competitive, as in they look exactly the same almost. Not exactly, but they look very the same. So they're competitive. They're fighting each other. They look the same. They're trying to steal the same spot, etc. They're fighting over the same food. Like whatever example you want to make that works for you. And because they're fighting, whoever is stronger will win. So the higher the substrate, that's good. If the higher the substrate, you can actually overcome the inhibitor. You can beat it. You can fight it and win. Okay. This is your example, HMG CoA reductase. And the graph again, just I hope this makes sense now, so I won't waste more time. Non-competitive, okay. Non, you're binding to both ES and also the enzyme by itself, okay. That's it. And here is a graph for that. And here's the example, lead and heavy metal poisoning. And finally, uncompetitive is binding only to the ES. So it's hard to mix these two. Sorry, it's easy to mix these two up. I don't know. One thing you could say, I guess, I don't know how useful this will be, is non has more letters. It has three letters. Okay, it's binding to two things, enzyme and also enzyme substrate. Un only has two letters before competitive. Okay, un versus non. Anything that works for you, just make it stick. That's what medicine is about. Just figure something out which helps things retain and just stick by it. As silly as it may be. Okay, so that's what I use personally. Just the lengths of letters That's what I use for like enzymes and any type of, memory type of things. So yeah, and there's the graph for that again. If you have any questions, please let me know. Here's the QR code to get back on feedback, etc. And here are my contacts. If you want to throw out any emails, any questions on text, regarding this lecture, I'm more than happy to help. And if you have any questions regarding MOL, etc., then I'm also happy to help as well. Hopefully you guys benefited from this. And if you have any questions, please let me know. If you have any questions you want to ask right now, then I'm happy to answer.